Hi, welcome to another extreme value theory video. In this video, we're going to be looking at the content introduced in chapter 2.1 of the notes, which looks at the distribution of block maxima. So we'll begin with a summary of the main topics that were introduced. And there was quite a lot of material introduced in this section. So firstly, what we looked at was the limiting distribution of the maximum of a collection of random variables, x1 to xn, where these random variables are independent and identically distributed. And we considered the distribution of this maximum as the size of the set x1 to xn grew larger and larger. What we found was that this distribution converges to a point mass at the top end point of the distribution function for x, and that if we use a suitable rescaling of these maxima, if we linearly rescale the maximum using constants an and bn, then we can achieve a non-degenerate limit distribution, one that doesn't collapse to a point mass on that upper end point. While we're looking at this, we introduced the idea of equivalence classes of distributions that are the same up to type. And using this idea of equivalence classes of distributions, we saw that the rescaled maxima converge to one of four possibilities. The first is that there don't exist constants an and bn, such that we get a non-degenerate limit distribution, and the distribution of the rescaled mn still collapses to a point mass at the upper end point. The other more interesting case is where we can find these sequences of normalizing constants, in which case we have three possibilities. The limiting distribution is going to be of the same type as either a gumbel, a Frechet, or a negative Weibel random variable, and this result is known as the extremal types theorem. While it's a useful result in terms of probability, in terms of statistical modeling, it's not particularly useful because we have to work with three different probability distributions. The unified extremal types theorem gives us a way to work around this. It says that any of these non-degenerate limit distributions can be represented by a single parameterization, the GEV family of distributions. In the final part of this section, we looked at how this unified extremal types theorem is very similar to the central limit theorem, but it's referring not to the mean or the sum of random variables, but instead to the maximum. So what we're going to do next is look a little bit more in detail at the GEV distribution. The distribution function here is a bit hairy, so what we want to do is build up some intuition about what each of the three parameters, mu, sigma, and psi, are doing within this distribution. First of all, we'll begin with the shape parameter, and we have three different distributions shown here. In each case, we're keeping the location parameter, mu, fixed to 0, the scale parameter, sigma, fixed to 1, and all we're doing is varying the shape parameter, psi. When psi is negative, as shown by the blue curve here, the distribution is going to have a finite upper end point. We reach some value above which there is no probability density any longer. When psi is equal to 0, we have an exponential tail. So in the limit, as you go further and further to the right here, this tail will behave like an exponential distribution. And in fact, because we're looking at this special case where mu is 0 and sigma is equal to 1, above what this is going to turn into is an exponential 1 type tail. And finally, the shape parameter being positive tells us that as we look at larger and larger values, this distribution has a heavy tail. The distribution decays more slowly than an exponential distribution. And that's what you can see by looking at this red curve. the decay will eventually be sub-exponential. So moving on now to look at the location parameter mu, and all that does is shifts the entire location of the distribution function. So here again, we're looking at red, blue, and black, where blue is a low value for mu, red is a high value for mu. And you can see that keeping the shape parameter fixed and the scale parameter fixed, that increasing the location parameter mu simply translates our probability density function to the right. And finally, the scale parameter, and this should say sigma up here. What we're going to do here is consider fixing the shape parameter and the location parameter and increasing or decreasing the scale. What this parameter does is it controls how concentrated around the peak the distribution is, in much the same way that the variance operates for a normal distribution. So you can see here that for a small sigma value, the distribution is concentrated around its mode, and for larger values, the distribution becomes progressively more diffuse. So now looking on to some tasks to help you build some more intuition about extremal types and about this GEV distribution and its subclasses. The first task is optional, but if you have time, I highly recommend you take a look at it. And that's to go to the Moodle page and complete the code in the activity file exploring extreme value distributions. What this code lets you do is look in a very similar way to what we just have with the GEV, but at each of its subclasses. It'll get you to go through and plot the PDFs and CDFs of each of the three subclasses, a gumball, a fresh A, and a negative Weibel random variable, for a variety of parameters for each of these subclasses, and sort of build some intuition about what these distributions actually look like. The solution code is also provided in that folder, so if you're trying to work through this yourself, hold out looking at that. If you're a bit short on time, feel free to just browse your way through that solution code. And that's everything we have to cover in this video, and I'll leave you with a second task, this one focusing more on types of distribution. In the notes in section 2.13, there's a claim made that two normal distributions with different mean parameters and different variance parameters were equivalent up to type. What I'd like you to do is look back through the notes to find this claim and the definition of what it means for two distributions to be of the same type, and have a go at trying to prove this statement. In the next video, we'll walk through a solution to this. Thanks for your time, and I'll see you next time.